I think philosophy is about to be a growth industry again, because I think
that's good to hear.
As we find out that specialized knowledge, which is what a lot of kind of traditional scientific knowledge has turned into being, that a lot of that is automatable, and so the
Yes.
contribution of us humans becomes much more the global thinking thing, which is much more the province of philosophy than it is the sort of the traditional STEM fields and so on.
Hello, my geeslings. This is Mother Goose Robinson Earhart here with the introduction to Robinson's podcast, number 102. And this episode is with Stephen Wolfram, who's the founder and CEO of Wolfram Research and the creator of Mathematica, Wolfram Alpha, and the Wolfram Language. Stephen received his PhD in theoretical physics from Caltech at the whoppingly small, 20 years old. And in addition to his work at the helm of Wolfram Research, he writes and researches and publishes widely across computer science, physics, math, and more. And most recently, Stephen's the author of What is ChatGPT Doing and Why Does It Work? And that is the subject of this conversation. So we begin by discussing just this, before moving on to some more theoretical questions about intelligence in general and artificial intelligence in particular and computation and the Turing test. And then after a pretty long and, for me, really fun digression on the foundations of mathematics, computation, and physics, we turn to the ways in which ChatGPT may impact research in STEM fields and beyond. And in particular, I was curious about whether or not he believed that these large language models might impact mathematical research. And of course, we get to this. And even though I'd been using Wolfram Alpha for quite some time, I first encountered Stephen the person on Sean Carroll's Mindscape podcast, where I was pretty blown away by his intellect, his articulateness, just how knowledgeable he was about this huge variety of domains. And actually, of all the people I've interviewed so far on this show, Stephen and Noam Chomsky were the guests I've been most intimidated by going into the conversation. But Stephen was super kind to me and patient, and I really, really, really enjoyed talking to him. And I'm hoping that we can do it again soon, since he's written and worked on so many topics. But what is ChatGPT doing and why does it work is linked in the description, as is Stephen's website and Stephen's Twitter. And so is Wolfram Research on YouTube, because Stephen does these really great, really long Q&A sessions quite regularly. And he also has other conversations with other scholars on there as well. So I think I saw one with Nassim Nicholas Taleb, and there are plenty of others. So reviews, subscriptions, comments, likes, all of these things are endlessly appreciated. And now, without any further ado, I hope you enjoy this conversation as much as I enjoyed having it with Stephen. Since it's likely that some or many of my listeners won't be familiar with how ChatGPT works, and since you've just written a book on the topic, what is ChatGPT doing and why does it work, I think it would be nice to quickly give a synopsis of how ChatGPT functions before we get into some of the more substantive questions I had in mind about minds, intelligence, and large language models. And since I know you could describe ChatGPT, though, on many levels, from a linguistics perspective, a computational perspective, a UI perspective, I think for our purposes that it would be best to keep it quite high level and perhaps just say a bit about the model's training, and maybe if we were to attribute intentionality to it, maybe what its goal is when a user inputs a prompt.
So let's talk about what it actually does.
Sure.
Okay. It's producing text. And the way it works is you give it a certain piece of text and it tries to figure out how that text should be continued. What does should be mean? How that text would reasonably be continued to match up with the things that it's seen from reading a trillion words on the web. And so its underlying operation is you've given a block of text and it's trying to figure out at every stage what should the next word be.
Mm-hmm.
And it has a neural net that is kind of a model of sort of what's out there on the web that tells it, the probability that the next word is, I don't know, let's say the previous words were the cat sat on the, what's the next word? Based on what's on the web, it might be there are 50,000 instances of mat, 3,000, 13 instances of sofa, one instance of podcast,
Mm-hmm.
this kind of thing. And so, the first level is just based on what we humans have put out there on the web, what is the kind of collective sort of idea of what language is, then emulate that. Now, there isn't, in fact, enough text out there on the web to just be able to count instances of this piece of text. So it has to have a model. It has to have some way of extrapolating beyond its mere experience, so to speak. And, the model it has is a neural net that has, 175 billion weights, about 400 layers of neurons, mathematical neurons. And there's an important question of why such a model actually produces text that seems reasonable to us humans. And I think the fundamental answer is because the way that neural net is set up is pretty similar to the way the neural net in our brains is set up. And in a sense, it's telling us an important fact about neuroscience that ChatGPT does a decent job. It's telling us there isn't more to brains at the level of generating language than this thing that can be represented by this kind of idealized neural net. But in terms of what is it doing? Well, there's a real question about why a model like this can work. Why is it the case that this sort of incredibly potentially kind of conceptually rich thing of human language can be captured by such a comparatively finite system? And I think my main conclusion is something which I think is sort of scientifically interesting, which is, we're very familiar with the idea that there are kind of rules of language that are associated with syntactic grammar.
Mm-hmm.
Sentences are composed of nouns and verbs and other, things like that. But that having a syntactically correct sentence doesn't say that the sentence means anything at all.
Right.
It could be some sentence that's just a jumble of words that happen to be the right parts of speech. Well, so the question is, what's a thing that determines the pattern of words that can mean something? And I think a great example sort of from ancient times is logic, which, my version of kind of what Aristotle did, I don't think we know what he actually did to construct logic, but, he looked at a bunch of rhetoric, looked at a bunch of text, and abstracted from that text certain patterns that were repeating, which corresponded to the patterns of syllogistic logic. And that's what, for a couple of thousand years is what people thought of as kind of this formal structure that's kind of erected above language, where, you can say, it was raining today, the cat is black, doesn't matter what the statement is, it still has the kind of the structure of how that statement relates to others is determined by the formalism of logic. So I think the thing that ChatGPT is kind of showing us, one, it's showing us that kind of brains don't have some magic quantum thing in them that is beyond the kind of the structure of something like a neural net. And second of all, that language is sort of, there's a way, a construction kit for language that goes beyond what we knew already. And frankly, could have been, people studied this a bit in the 1600s in the kind of tradition of philosophical languages and so on. It's been studied only microscopically in more recent times. I was kind of shocked recently to realize that a lot of what people had done, in the early 20th century and going back even to the 1600s, I was like, these people did something original at this time. And then I thought, I better actually look at what Aristotle did. And Aristotle doesn't say a lot about this, but what he does say is kind of directly in the line of what got done later. And, it's very incomplete. But I think that's kind of one of the things that comes out of this. Now, in terms of, you say, can one attribute kind of a mind to this thing? Right? That might be a question you could ask. Can you, in what sense is there in a sense, it is a reflection of the sort of statistical average of human outpourings. although that's not that different from the way that we use language. I mean, language, to be useful, has to be something that is kind of used in a common way by lots of people so that it's a means of communication, so to speak. And I think, but, if you ask the question, one of the things that for me has been useful is a lot of my life has been spent trying to create a computational language to try and sort of represent formally things in the world. It's kind of a vast generalization of what one might think of as, logic representing, we're trying to represent chemicals and movies and cities and the relationships between them and so on in some precise computational way. So one of the cases where you say, does the machine understand what I'm talking about? In the case that we have in, for example, our Wolfram Alpha system, we're going from natural language, and what we mean when we say it understands is we can translate from natural language into our computational language. The computational language is then this precise specification of what one is talking about, precise in the sense that you can build this whole tower of actual computation from that specification. So in a sense, that's you say, does it really understand? Well, the answer is with a large language model, not in that sense. But, we have technology we've built to go from computational language. And by the way, large language models can prime this a lot. But to go from natural language to computational language, and at least then we can sort of say, in some sense, our computers understand. We have there's a precise thing from which you can then go and work out many consequences.
Mm-hmm. Well, I wanted to get to understanding eventually, but for now, I'd like to stick to the similarity and connection to the human mind that you brought up a bit earlier. And I personally haven't used ChatGPT much, but despite some of the immensely impressive things it can do. So after listening to an episode I did about the set theoretic multiverse, my dad had ChatGPT write a sestina about Hilbert's Hotel. I have the sense that in general, we wouldn't consider it capable of passing the Turing test at this point. And again, for those who aren't familiar with it, what I have in mind here is just whether or not somebody could communicate with ChatGPT unknowingly maybe and be unable to tell whether or not it's human. But at this point, do you think it is particularly far off from that?
I think there are many situations in which you wouldn't be able to tell it isn't human. I mean, if you know ChatGPT and you know the kind of rather anodyne kinds of prose that it tends to produce, you might say, hey, that's a bot. Uh-huh. But I think in many situations, you're doing some, chat customer service interaction with somebody. I'm not sure you'd be able to tell. And I think, it depends. Right. If you probe it in certain ways and you see, well, it's giving kind of a bland answer to this, it's like, that's probably a machine because it's, most people would be a little bit more, would have a little bit less blandness to their answer. But I think it's in terms of language as a kind of, it's a pretty good simulation of what we humans produce as language, up to some level of kind of originality, creativity, and so on. It's as I said, it's a little bland relative to what folks like me aspire to in terms of the things one writes.
Well, the reason that I ask, and I promise that I'm heading somewhere, it's a bit more abstract than just ChatGPT, but I wonder whether you think we would be willing to call something like ChatGPT, maybe like a future iteration of it, intelligent, simply because it was indistinguishable from a human interlocutor in a case where we are probing it with more intention, whether to determine whether or not this is the case.
Yeah, well, I mean, this is always, it's sort of a disease of philosophy, right? You have a word like intelligence, and you say, do you consider it intelligent? Well, it's kind of just a word. And, the question is, what comes with that word?
Exactly.
And, what does it, I have to say, in by way of personal history and things in philosophy, my mother was a philosophy professor in Oxford. And so I was exposed in my early life to lots of philosophers, and I kind of I always said, if there's one thing I'll never do when I'm grown up, it's be a philosopher. And hasn't quite panned out exactly that way. But this was always a thing which, somehow in conversations the very young me would have with the well, at that time I thought ancient philosophers, but probably younger than me now, it would often come up, there's some word, there's something, what is X? And it always kind of drove me crazy, because it's like, it's just a word. And, words come with a certain baggage of what they might mean to people, which you kind of have to have a consequence to that word to really lock in, what are you really talking about? So in terms of intelligence, I've been interested in kind of what is intelligence, so to speak. What is intelligence versus what is merely computational? And I think one thing that is true of kind of, you don't get something that we'd reasonably call intelligence without some level of computational sophistication.
Right.
If you've got a thing that's just repeating, periodically doing the same thing, you're not going to end up calling it intelligent. But there are, one of the things I've been interested in from a science point of view is, what are the levels of computational sophistication of different kinds of systems? And you might have thought, oh, a brain, it's got all this sophisticated stuff in it. A modern computer, it's got all this sophisticated stuff in it. It must be computationally more sophisticated than some simple abstract system, than some system in nature, things like this. One of the big consequences of a whole bunch of science I've done is that no, there aren't different levels of computational sophistication. Once you get above some threshold, there's this kind of principle of computational equivalence that I came up with that kind of implies that there's this sort of vast equivalence between the kinds of computations different things can do. So it's kind of like the old statement, the weather has a mind of its own. That's, in this way of thinking about things, the weather is computationally as sophisticated as brains, which are correspondingly computationally at the same level as even simple abstract, rule-based systems and so on. And so, I think that this base level, this sort of underlying requirement of what counts as intelligent versus merely computational versus, you have to have this layer of computational sophistication before you can reasonably get to this point. I mean, I would say, just as a matter of sort of a footnote, of perhaps amusing footnote, this whole question about what is intelligent versus what is merely computational, which you might say, well, that's sort of a philosophical question. For me personally, that became at some point in my life an incredibly practical question, because I've been long interested, ever since I was a kid actually, in kind of, can one take knowledge in the world and kind of make it what I would now say computational? It's not the term I used back in those days, but can you make it kind of something where you can automatically answer questions? Well, back in the mid-aughts, I kept on revisiting this question, and I had always thought to make something which was a good sort of expert answerer of questions according to the corpus of knowledge that we have in our civilization, that we would necessarily have to build kind of a brain-like thing, a general artificial intelligence kind of thing. But after I developed this principle of computational equivalence, kind of came back to that question, I said, look, this principle of computational equivalence says there isn't really a bright line of the intelligent versus the merely computational. So I have no excuse for not trying to actually build a practical system that does this kind of question answering. And so it wasn't clear it was possible, but, we started building that, and indeed we built Wolfram Alpha and so on, and turns out it was possible. And so this idea that there isn't kind of a spark of intelligence different from the merely computational, for me, had this very practical consequence. And I think, perhaps the thing we built gives a little bit more evidence that no, there isn't really this huge distinction. And I think now with ChatGPT and so on, we have another sort of piece of evidence that the merely computational, that there isn't some sort of spark of difference between the intelligent and the merely computational. But I think the other thing to realize is, what is the difference between us and the random simple rule-based system, the weather, whatever else? The answer is a ton of kind of specialized, kind of the way that we are versus the way generic computation is. And that isn't something that seems to be a different level. It just seems to be a different set of particulars. We have the particular set of words in our language. We have the particular collection of common sense knowledge based on kind of our experience of the world, our sensory experience, et cetera, et cetera, et cetera. Those are things that we have that are particulars. They're not a matter, I think, of, we are better than the weather or something like that. We are just have different particulars which lead us to have, to experience something where we've got this kind of, these computational things are things that have sort of human-like characteristics, and other things might be just as, quotes, intelligent, but not human-like.
So I'm particularly curious about when you were saying that there was no line that you could determine between the intelligent and the computational. And what I'm wondering is, when you began, you said that you pointed out that intelligence is just a word. And are you explaining in explaining that there is no line between the intelligent and the computational, is that to say that there is nothing really substantive behind the word intelligence?
Right. I mean, so I think, yes, I think the answer to that is yes, that's what I'm saying. Now, a thing that I've realized only in the last couple of years, 3 years or so, through a very circuitous route, I've realized when, I'd always thought, you talk about consciousness, I'm always like, that's a horrifying term. I don't know what it means. It's all mushy, et cetera, et cetera, et cetera. But because I've been interested in fundamental physics and understanding kind of how we build the whole universe computationally, so to speak, and how that works and how to think about that, one of the things that's come out of that, which I think is an incredibly beautiful piece of, I don't know whether you call it science or philosophy or something else, is this kind of ability to derive kind of the laws of physics as we know them. But that derivation, and we can talk about it in more detail, but that derivation is kind of you start with kind of this thing, we call it the Ruliad, this entangled limit of all possible computational processes. It's kind of this unique kind of object that encapsulates everything possible computationally. And then the question is, how are we, as observers of that, how are we sampling that thing? And the answer is, we have certain characteristics. We have certain specific characteristics as observers. One of the characteristics is actually the opposite of saying we've got lots of computational sophistication. It's that we're actually computationally bounded. We don't get to follow every detail, work through every computation that's going on in the Ruliad. We are just sort of sampling the small pieces. Kind of like if we are looking at something like, molecules bouncing around in a gas, we don't follow every individual molecule. We simply sample some aggregate properties of the gas. And the whole point is that we're sort of limited in our computational abilities. It is not that we are more powerful in the universe. We're in a sense a subset of what the universe could provide. And turns out that kind of narrowing is critical to the fact that we observe the laws of physics that we observe. I mean, there's another criterion that's necessary for deriving the structure of space-time and the structure of quantum mechanics, which is an interesting thing, which is, in addition to us being computationally bounded observers, that we're also observers who believe we are persistent in time. And that's a thing that is kind of, even though we might be made of different atoms of space at every successive moment, we believe that there is a continuity to our thread of experience. And that belief kind of feeds into the way that we understand how the universe works. But so to this question about, is intelligence, or something that we might intuitively think of as intelligence, is it merely computational? I would say I would add the footnote. It's actually a bit of a subset of all possible computation, so to speak. We have these features like our belief in persistence in time, like our boundedness in terms of the computation we can do relative to all the computation that can happen in the universe. So, I mean, those are specifics, but I think beyond that, the thing that makes us, what is human-like intelligence versus what is intelligence in the abstract. And I think human-like intelligence has a lot of features of kind of our details as humans. And that's what you might mean when you say intelligence is kind of human-like intelligence. I think that as soon as you get beyond the kind of human-like intelligence to something more general, you're pretty much thrown into this sort of vast ocean of what's computationally possible.
Mm. And I just want to make sure that I heard you correctly. You said that a few minutes ago that whether or not there is really something substantive behind intelligence, you said that the intuition behind what we mean by the intelligent is captured by a subset of the computational. Is that roughly what I heard you say?
Well, okay. So I think human-like intelligence
Mhm.
is a subset of what is computationally possible.
Okay.
If you ask me about non-human-like intelligence, I'm not quite sure what to say.
Okay. Sure.
I'd like to, that's where we should bring your cat into the conversation.
Yes. Yes.
It's
But no, this is exactly what I was wondering. And returning to my initial question that sort of sparked this, it wasn't really a digression, but this talk about what intelligence is. Do you think then that passing the Turing test, in which a human is trying to probe and determine whether or not the being it's speaking with is a human, does passing that confirm that that what it's speaking with is part of this subset of the computational that characterizes human intelligence?
What is it like to be human-like? Well, we can say it's really important that you have two eyes, that you walk in this way, that you respond to an optical illusion in this way. I think that if you say, is this thing truly human-like? Then the answer is, if it's a bunch of semiconductor, things, it's not truly human-like. When you say, is it human-like at the level of being kind of intelligent like a human, there are lots of frayed edges. I mean, it's going to have, you can have a conversation with about mortality, for example, and it might just, in the case of an LLM, it's going to parrot what it read on the web about mortality. But in terms of, you can push it in such a direction that, the fact that it isn't physically like a human is going to become evident. And then you'll say, well, it's not human-like. But yeah, well, that's because it's not a human, so to speak. So I think that if you say, is it, defining, Alan Turing's narrow kind of version of nice, but narrow version of, what it might be like to be able to tell, is this a human-like intelligence? I'm not sure what we would conclude beyond, yes, it's a human-like intelligence as defined by the Turing test, so to speak. Does that mean that it's truly human-like in all respects? Obviously not.
Okay. This is where I wanted to go, because granted that you never wanted to be a philosopher, there is an interesting paper in the Philosophy of Mind by the philosopher Ned Block. Are you familiar with this idea of the quote unquote the blockhead?
Nope.
Okay, well,
Educate
yeah,
me.
sure. It's an attack on this behaviorist conception of intelligence, so that we could determine whether something is intelligent, or even maybe you'd be more sympathetic to intelligent in a human sense, just by observing its behavior and without
Mm-hmm.
any reference to its internal processes. And the argument is supported by, and I think really demonstrated through, a thought experiment that involves this machine called the blockhead. And we are told to imagine a team of researchers with infinite time and budget, and you might want to object to that immediately, but they draft up all of the possible sensible conversations that could transpire between two people in, say, an hour, just for the sake of a reasonable rendition of the Turing test. And these conversations are structured kind of like a play. So in terms of input and output, you have like respondent, terminal, then this corresponds to input and output. And they then set up this machine, which has hence been known as the blockhead, so that it takes the initial input that's typed into it by the participant in the Turing test at the computer terminal, and then it combs through its database of all of these conversations. And it selects a conversation that begins with precisely that string, and then it outputs the next response. And the participant responds, and then the blockhead, it again.
Yeah, I understand. It's enumerated all possible conversations, and it can just match it up.
Right.
Yeah, I mean that's a kind of an idealized picture of what an LLM does.
Right. And except of course the LLM it's generative in a certain way, and it has much more sophisticated pattern recognition. But the idea is that the blockhead, even though, because we know how it works from the outside, we know that it is not at all anything we would consider intelligent, but it still will pass the Turing test as regularly and predictably as a human. And this argument is supposed to demonstrate that we cannot determine whether something is intelligent at all behaviorally.
So I think that the key thing that's being missed there is the phenomenon of computational irreducibility, which people tend to, I mean, actually, since I invented this concept in the early 80s, there is actually a decent philosophical literature about it. But it is something that will be seen as increasingly important in understanding kind of how the world works. It's kind of a foundational idea in thinking about how the world works. And what it has to do with is, you know the rules by which something operates. But the question is, does that then mean you know everything about the thing? Mm-hmm. And the point is that what one discovers is that it can require an irreducible amount of computation. If you want to know what is the system going to do after 1 billion steps, well, you can just run the 1 billion steps of the computation and find out. But is there a way to jump ahead? Is there a way to computationally reduce things? And that's what, a lot of kind of the science that started in the late 1600s and so on, the kind of mathematicized science, is all about, look, we can predict, we can jump ahead of the actual operation of the system and say what's going to happen. But it turns out that there are a great many systems, in fact, any of these systems that show this kind of computational equivalence property, there are a great many systems where you can't do that kind of jumping ahead. So when you say, oh, we're just going to enumerate this finite collection of conversations and so on, well, yes, in that box, you can say, sure, you can tell if you only talk to it for 15 minutes, you can have enumerated all those conversations. But if you consider the unbounded case of what's it going to do eventually, what's it ever going to do, that's what you realize is, yes, you may know the rules, but that doesn't tell you it doesn't, you think, because I know how this thing was constructed, that therefore you've kind of nailed everything about it. And in the particular thing you're talking about, because it's of finite length, you can kind of just enumerate all the cases. You don't have to worry about kind of unbounded computations and so on. That's, take away that restriction. You don't get to say, oh, we can just enumerate all these cases and know that they're sitting there in the box, so to speak. Then you have to start saying, well, I've got this team of experts and they're enumerating these things. And look, I can see these experts are just using rules. And these rules, they seem very simple. They don't seem consistent with there being a magic spark of intelligence there. But the truth is that all, from what we've figured out about physics, for example, all the way down, it's just simple rules. So when we say, well, we just, as soon as you can say, look, I can see these rules, they're simple. Look, there's no spark of intelligence here. Well, that's our universe. And this phenomenon of computational irreducibility is what kind of irreducibly separates the actual behavior we see from the sort of external description of, look, we put these rules in, and all we're getting is these rules we put in, so to speak. So I think the mistake there is, the key conceptual mistake is not thinking about computational irreducibility, not thinking about, just because you know the rules, you say, therefore I know everything. That's just not right. And, so, I mean, that would be my response. I learned when I was a kid that philosophers, their form of interaction is one person has a theory and then somebody else says, no, that's wrong.
Yeah.
And then they all, cheerfully go out to, the pub or whatever afterwards, and then even though they were vigorously attacking each other. But that would be my immediate response. I mean, I've not heard that particular story before, but that would be my immediate response
No,
to
that's
that.
good. I interviewed this very famous number theorist at Columbia, Michael Harris, who's very, very interested in philosophy as well. And he said that as far as he can tell, the way philosophers work is that they just try to trash everybody else's theories. And that's how philosophy progresses. But
Yeah, when I was a kid, I always said, any field where you're still arguing about things that people talked about 2,000 years ago is a field where no progress has been made. It's a field where, but I think actually maybe we'll talk about it later. We'll talk about mathematics perhaps and progress in mathematics. I think in half a century later, I have a slightly more nuanced view of what I think progress means and so on. But okay, that's
that is
a
something
digression.
that I would like to get into eventually if you want to, because I've had a number of episodes on the podcast precisely about progress in mathematics and whether or not there are genuine revolutions. But as far as philosophical progress is concerned, I'm in agreement with you in that it does seem like every philosophical program fails, and I'm taking a number of ancient philosophy courses at the moment right now, and we are very much discussing the same problems that we discussed 2,000 years ago. But at the same time, biology, physics, all of these disciplines began with philosophy, and then once there was some
Absolutely.
sort of tractable methodology for solving problems, they then became their own special sciences. And it's the same with mathematics. So I don't think it's entirely fair to say that there isn't progress in philosophy. It just sort of
No,
changes.
I think one of the things that I found interesting recently is, I think philosophy is about to be a growth industry again,
Oh, that's good to
because I
hear.
think as as we find out that specialized knowledge, which is what a lot of kind of traditional scientific knowledge has turned into being, that a lot of that is automatable, and so
Yes.
the contribution of us humans becomes much more the global thinking thing, which is much more the province of philosophy than than it is the sort of the traditional STEM fields and so on. I think the thing I've realized recently is that kind of computation is kind of a lifting of and what we see even with large language models and semantic grammar and all these kinds of things is again a lifting out of the philosophical discourse into something more formal, of something which has long lived in the kind of domain of philosophical discourse. So I think that's that in a sense is I agree with you that philosophy is this kind of primordial vat from which all kinds of other more formal, more the ability of something like mathematics or, many of the physical sciences and so on to build this tower of sort of formal tower is something that, philosophy is still arguing back and forth in the kind of primordial vat. And then when you start having a formalism that lets you build kind of a real tower is when you kind of emerge out of that vat. And I think that's happening in a whole range of areas where we might not have expected it to happen as a result of kind of the computation idea. Computation is the modern vast generalization of kind of what I think happened with logic as a kind of an early example of formalization back in the day. But I think, I mean, in this whole question, I mean, to me, it's often interesting that, at the beginning, the discussion is a philosophy, ethics discussion, something like that. In the end, you've got to write a piece of code that does something.
Mm-hmm.
And so, philosophy to code is a very kind of, it's a funny thing, because I know in my own sort of life and times, I spent a lot of my life building computational language, and a lot of these questions that, my mother worked on all these questions in philosophical logic about identity and all this kind of thing. And it's like, who cares about this? I said.
Mm-hmm.
And then I realized that, when you're dealing with, I don't know, you have a lambda expression and it's got bound variables, and there's another lambda expression and, it's got other bound variables, and what are they the same? Are they not the same? What does this mean?
I'm doing that right now,
And you're
actually.
throwing, What's that?
I'm doing that right now, actually, in
Right.
computability and
So
logic.
right. So you're thrown right into that. A lot of these kind of old philosophical issues. Another thing that's been interesting to me in thinking about fundamental physics and kind of the foundational models of the universe is a lot of questions that had been, were kind of, well, for example, a question like, why does the universe exist? Which I have to say, I didn't think would ever have a kind of a hard answer. That question, now as a result of our physics project, we can actually discuss that question. And in I think, a very kind of hard, almost formal way. And I think the answers are fairly interesting. And I think we kind of have an argument for why the universe exists. But what I find interesting about that is that question is a question that has been kind of out of discourse for a few hundred years. It's something the theologians talked about back in the day. It's something that never really engaged with science. And now, as a result of kind of this sort of computational paradigm for thinking about things, we get to engage with a bunch of these questions that have been kind of out of science and only in philosophy for a long time.
Something you said that really struck me and that I think I might push back against a little bit is you mentioned that, and maybe I shouldn't be pushing back against it because you said philosophy would be a growth industry because of it. But you said that it would be a growth industry because a lot of the advances in STEM you suspect will be farmed out to machinery. And I already mentioned Michael Harris, but one of the main topics of our conversation was about automated theorem provers. And we also talked about aesthetics, which I think is important actually for the point I'm going to make. But he does not think that mathematics is at all in danger of being supplanted by computers because he sees mathematics as a very human undertaking, which is not how
He's right.
most non-mathematicians think of it. But for
Yeah,
him, mathematics is all about understanding. It's about beauty. It's not about just possessing a collection of theorems. We want to be able to
absolutely.
understand them. So,
No, mathematics is a deeply human sampling of all of what is computationally or mathematically possible.
mhm,
And it's almost it's an artistic sampling. I mean, one of the things I've been interested in is what I call the physicalization of metamathematics.
right.
So imagine you start from, in the simplest case, just start from some axioms. Just prove all possible theorems from those axioms. You get this giant, in physics we talk about light cones where
It's
some
like an
event happens
explosion.
and there's this region where light can reach it. Well, in metamathematics, there's an entailment cone where you start from this theorem, for example, and there's everything entailed by that theorem.
Mm-hmm.
So you have this vast number of theorems. And so now you have to ask the question, first of all, you say from a given axiom system, and then let's just say from all possible axiom systems. What are all derivable things from all axiom systems? A giant object. That object is this Ruliad thing that I mentioned earlier, which is kind of the entangled limit of all possible computations. Interestingly, it's the same thing that's underneath physics. But let's think about it abstractly as the thing that's underneath mathematics, the thing that represents all possible mathematics, all possible theorems, all possible axiom systems. We've got this big object. And now the question is, well, what do we care about in that object? How do we sample that object? And it turns out one of the first things you realize is we are human observers of that object. Mathematicians have certain characteristics. They have certain limitations, like computational boundedness, in their way of sampling that object. But I think to the point of what I think you might have been talking about with respect to mathematics and things like automated theorem proving, the point about mathematics, which I only realized fairly recently, is the mathematics that mathematicians care about is kind of a higher level mathematics. It's like in the analogy of fluids or something, there are molecules bouncing around underneath. Most of what we care about as humans about fluids is this smooth fluid dynamics that operates at a level of zillions and zillions of molecules, a much higher level of molecules. In mathematics, there is this kind of low level, push the bits around type mathematics that is very, go from these axioms and precisely prove with automated theorem proving this or that thing. But the whole point is that mathematics can be done at a fluid dynamics type level. In other words, you can talk about the Pythagorean theorem, and you can say, I'm going to deduce these things from the Pythagorean theorem. You don't have to sort of look microscopically underneath the Pythagorean theorem and say, oh, how did I define the real numbers? What are all the axioms here based on set theory and this and that and the other? Most of the time, you don't have to look down at that stuff. In fact, you just have to look at the level of the Pythagorean theorem and then prove from there. And that's kind of the main activity of human mathematics. Now, occasionally, you realize you fall down to this axiomatic level and you end up in a morass of undecidability and things like this. But the thing that is incredibly non-trivial about mathematics is that it's possible to operate at sort of this fluid dynamics level. It might not be the case. It might be the case that whenever you try and do mathematics, you are necessarily shredded down to this kind of atomic level, that there isn't a kind of higher level description of mathematics, that it's the only thing you can do is to build, step by step, axiom by axiom, so to speak. And I think one of the things that's a conclusion of my efforts in physicalization of metamathematics is that phenomenon that there exists a higher level mathematics, that it is possible to do mathematics at this non-atomic level, happens for the same reason as the fact that we can perceive space as continuous. We don't always have to be looking down to the atoms of space to know how things are going to work. And these are both aspects of us as observers with our limitations, observing sort of a slice of this Ruliad object. And I think, so in the way I view mathematics, it's kind of like this, mathematician is gradually deciding, these are theorems I think are true. They're sort of putting them in a bag. They're finding that there's a big entailment cone from those theorems. They're picking which ones of the things in that entailment cone are ones that they think are humanly interesting. One of the things that's kind of fun that can happen is, what happens if you put a false theorem in your bag? What happens if you, and then, there's this principle from the Middle Ages, the principle of explosion.
Exactly.
The material implication, if you start off with a false premise, you can deduce everything. Mm-hmm. So what happens is your bag bursts because you put this false theorem in and you're generating all possible theorems. And so you, as with your finite mind, thinking, oh, I know what's true, so to speak, you'll always be overrun by this kind of, gush of all possible theorems. So that's an example of it. It turns out to be analogous to the phenomenon of white holes in general relativity and in physics. It's the same kind of sort of formal phenomenon. But to your point about things like automated theorem proving, here's an amusing fact about automated theorem proving. So it's one question is, did anybody ever discover anything with automated theorem proving? Automated theorem proving is a way of dotting the I's, crossing the T's of things we sort of already knew. There's one example, which is something I discovered in 2000, which is I was looking for what's the simplest axiom system for Boolean algebra. And it's not obvious how simple it would be. You look at the axioms you find in logic textbooks, they've got things about ands and ors and so on, and you can do everything just in terms of NAND or the Sheffer-Stroke operation. And the question is, how simple is the simplest axiom system? Well, the answer is, which I found by automated theorem proving, it's about the 50,000th axiom system you get to. If you just start from, if you just start enumerating possible axiom systems in sort of order of complexity. And that's what is a little disappointing there is, you have to have a conceptual framework to know why you would care what the simplest axiom system for Boolean algebra is. But automated theorem proving is a very desiccated activity, really quite separate from the kind of what I might describe as the fluid dynamics level, the fluid level of mathematics, so to speak, which is the level that most, not all, but most working mathematicians find interesting. And that's kind of the human sampling of this Ruliad and the sort of human set of choices that get made about what one finds interesting in mathematics. But I think I interrupted you, but I had to jump in there because this is a great topic.
No, that's fine. Now that we've entered the philosophy of mathematics, I have, 1,000 questions, but I'll start with one very small question before I have a more substantial one. I have not heard this word Ruliad before, so I'm guessing that many of my listeners haven't either. So before we continue, just what is a Ruliad?
Right. So there's not a Ruliad. There's only one Ruliad.
Okay.
So it's a term I invented at what is it, a couple of years ago now. It's, okay, let's see. We probably have to descend, to really understand it, we have to descend a couple of levels in a rabbit hole.
Okay.
But let me say what the sort of nominal definition is. The nominal definition is, it is the entangled limit of all possible computations. What do I mean by that? So let's say you have a Turing machine, simple idealized model of computation. You have this Turing machine. You start it in all possible states. You look at the Turing machine, just does what it does. It has rules, it just keeps running, does what it does. So you start in all possible states. And what you can then do is you say, for this Turing machine, let's say there are two different states of the Turing machine at the beginning. Maybe they merge sometime later. So that can happen. And you're kind of mapping out what are the processes that go on that go from state to state. Okay, so now you don't just think about one Turing machine, you think about all possible Turing machine rules. And in that situation, you start off from one state, and you can apply one Turing machine rule and it goes over here. You apply another Turing machine rule, it goes over here. Now, maybe subsequently, the states, those two different states, will apply some Turing machine rule, they'll merge. So you get this whole structure of branching, merging states of, let's say, Turing machines. Then you continue that for all time. You just keep it running forever. And it then turns out it doesn't matter that you're talking about Turing machines. It's just a change of coordinate system. It's like rotating coordinates, and you're still talking about the same piece of space, so to speak, but you're describing it with different X and Y and Z values and so on. So you could change from Turing machines to cellular automata to other, all kinds of different models of computation. This limit will always be the same thing. So this limit is sort of interesting because it encapsulates all that is computationally possible, and it is unique. There's, you can describe it in different ways, but there's just one Ruliad. Mm-hmm. The only way that it isn't unique is to say, well, it only uses Turing machines. So a Turing machine has certain limitations. Like, for example, if I say, and it's related to computational irreducibility, if I say, here's this Turing machine, is it ever going to reach some halt state? You say, well, I ran it for 1 million steps. It didn't reach a halt state. It's not going to halt. But it is not in general possible to prove with a finite proof that the system will eventually halt or not. And this is a feature of computational irreducibility. I mean, just to give the logical flow of this, the most fundamental principle here is the principle of computational equivalence. The idea that systems are equivalent in their computational sophistication. So then the question is, if you have a system and it's running according to certain rules, and you are saying, I'm going to jump ahead, I'm going to predict what the system does without having to follow all those steps. Well, how are you going to do that? Well, eventually, you have to be somehow computationally smarter than the system itself. You have to be able to say, well, it spent 1 billion steps, but I've got this really clever computational technique that lets me answer that in 3 steps. Okay, but the principle of computational equivalence tells you can't do that. It tells you as a brain, as a mathematician, as whatever else, you are simply computationally equivalent to the system that you're studying. And so that's why you get this phenomenon of computational irreducibility. So that's kind of that's that piece of it. Now, when you're looking at, but one thing you could say is, okay, well, computational irreducibility is something where you can't jump ahead because you're just computationally equivalent to the system. But I could just say, I just imagine that I have what usually gets called an oracle. Imagine I just have this box that answers questions which take an infinite time for a Turing machine to answer. And you just say, I'm going to attach this box to my computer. Well, with that box, you can go beyond mere computation. You can go to hypercomputation. So there are an infinite hierarchy of hyper-Ruliads which involve more than just ordinary computation. But the one sort of contingent fact, I think, about the universe is we live in the Ruliad and not in the hyper-Ruliad. And there is a necessary event horizon, kind of a causal disconnection between the Ruliad. There's the same kind of causal disconnection between the Ruliad and the hyper-Ruliad as there is between what we see in the physical universe and the interior of a black hole. It has the same kind of causal, you can't have an effect going from one to the other type thing. So it is not self-evident. It's not something we can prove in some sense that we can find empirical evidence that we're in the Ruliad and not in the hyper-Ruliad. But it's the same. It has the same kind of status in kind of thinking about what's necessary and what's not, as to say, we are at this place in the physical universe. There's not a thing where you can say, I'm going to prove a theorem that the Earth is at this place in the universe. That doesn't really make any sense. It's just we happen to be at this place in the universe, and given that, we have certain impressions about how the universe works. Well, we happen to be in the Ruliad and not in something else, but there is only one unique Ruliad. And so then you ask the question, well, so for example, there are many, many questions you can ask. So the important thing is we are sampling the Ruliad at one place in the Ruliad, which means that, among other things, we have, given the way our minds work, given the way our senses work and so on, we have a particular view of how the universe is working. If we were to move ourselves to a different place in Rulial space, sort of a different place in the Ruliad, we would have a different point of view about how the universe works. It's still the same underlying Ruliad, but we're sampling it in a different way. Just like in physical space, we can move from here to there and we'll have a different point of view about what's happening in the universe. So in this case, what we're the way I see it actually, and this is sort of a philosophical prong that is not 100% worked out, but the way I think of it is, different minds are at different points in the Ruliad. They're different points in Rulial space. So, you can be physically in a different place and you have a different point of view about things. You can be in a different place in Rulial space, which means you have a different view of, you attribute different rules to the way the universe works. And it's just like, in my mind versus in your mind, we might think we're talking about the same thing, but the actual internal operation of our minds is quite different. Mm-hmm. And so one of the things that's really kind of fun, that is a place where sort of you see a contact between physics and all of this stuff, is in physics. One of the remarkable things in physics is that pure motion is possible. That is, you can take an object and you can move it somewhere and it's still the same thing. It's not obvious that will be true. If you happen to move it very close to a space-time singularity, it won't be true. Mm-hmm. But in most of space, you move something from here to there and it's still the same thing. There is a sense in which the identity of the object is not changed. By the way, in mathematical space, that same kind of preservation of identity under motion, I think, is the reason that there are these big dualities between different areas of mathematics. You can think of different areas of mathematics as existing in different places in meta-mathematical space, and this kind of idea that sort of you can move from one to the other is kind of like the algebra to geometry translation, things like this. But back to physical space. So we have this idea of motion in physical space, the possibility of pure motion. The question is, what are things that are subject to pure motion? So, for example, particles like electrons. Electrons preserve their identity while moving through space in the course of time. And this is, so in a sense, we can think of an electron as being some sort of, well, in our models of the universe, everything is just made of space. Space is, I should say this is, I'm sort of bizarrely ascending some rabbit hole. I started from the Ruliad, which is kind of the bottom of the rabbit hole. But sort of a fundamental piece of our, just to outline this because it's relevant to the intuition of these other things. In our kind of current theory of fundamental physics, I say our, this thing that, I'd been working on it from the 1990s, but really got developed in about 3 years ago now. And it's now become, I would say, a decent number of physicists and mathematicians are working on it, and it's sort of becoming a bigger snowball. And it's very, very, very beautiful. It just came out more beautifully than I could ever possibly have imagined.
No, I can tell the way that you talk about it. It's like a child.
Yeah, right. Well, it's kind of like, I had no idea that, for example, the three fundamental theories of 20th century physics, general relativity, the theory of space-time, quantum mechanics, and statistical mechanics, the thing that leads to the second law of thermodynamics, all three of those theories can be derived from the same principle. They are, in a sense, the same theory. And I had no idea that would come out that way. And it's really, to me, it's just an amazing thing. And really, all three of those theories, we can talk about it, are the results of the interplay between the way we are as observers interacting with this underlying Ruliad object. Mm-hmm. But just to start off from kind of the theory of physics, the starting point is, one important point is space is discrete in our model. So, people have imagined ever since Euclid and so on, space is just this thing where you put stuff at different positions in space, and you can put things anywhere you want in space. Well, back, in ancient times and so on, people wondered, is matter continuous or discrete? And, for a long time that was unclear, and it became clear at the end of the 19th century that matter was actually made of discrete molecules. And then, another big surprise, the electromagnetic field, light and so on, is also made of discrete particles. At that time, at the beginning of the 20th century, it was like, well, presumably space is also discrete. But there were technical reasons why people didn't manage to make that work. I mean, Einstein famously, at least famously to me, had this statement back from 1916, said, in the end, space will turn out to be discrete, but we don't have the mathematical tools to understand how this will work yet. So 100 years later, we do. Mm-hmm. And turns out that it is, so the starting point is realizing space is discrete. It isn't the case you can just put things anywhere you want. Just like, you have water, you can't say there's a piece of water everywhere. There's only sort of water where there's a molecule type thing. So space is discrete. Everything that is in the universe is a feature of space. And we have this kind of a good way to think about the structure of space is it's like a hypergraph. You have these atoms of space, just these points, disembodied points, and all that you can say about them is how they're related to other points. You're building up this kind of graph, this network of connections between the atoms of space. They're not placed anywhere particular. All they know is they have these relationships between them that are defined by these relations associated with this graph. And that's the structure of space and everything in space. So, for example, just like in a fluid, you might have a vortex. When you run your finger through the fluid, you'll see a little eddy. That eddy is made of the exact same molecules as make anything else in the fluid. And so similarly, a particle, like an electron, we think of as being something a little bit like an eddy, but now in this graph that represents the structure of space rather than in this bunch of molecules bouncing around. So an important point in this kind of picture is what is time. And in this model, the graph is continuously getting rewritten. There are rules that say if you see a piece of graph that looks like this, it's going to change into one that looks like that. And so there's this progressive computation of new graph from old graph, and that computational process is the progress of time. And computational irreducibility is the reason that there's sort of something definite happening in the progress of time. And it's so we kind of have this idea space is a very different kind of thing than time. And, relativity still works out. It works out very beautifully. It's an emergent feature of how the system works. It wasn't something, space and time start very different, but they still have this relationship that relativity implies and so on. But then the next thing to realize is, so we got this system, it's evolving through time. And then the next thing you realize is, well, there are all these different rewrites that could happen on this graph. There are actually many different rewrites that could happen to a given graph. There are many different rewrites that could happen next. And that means that time is not a single thread. Time is this multi-threaded thing that has both branching and merging. And so then it turns out that quantum mechanics is the feature, is a consequence of this fact that you get these many threads of time. And one of the strange features is, one of the critical things about this model is that we are embedded within the model. So we have to think, what does an entity embedded as part of this model think about what's going on? So, for example, an important feature is there are many branches, there are many threads of time, but our minds are spread across many threads of time. So, in other words, it becomes this question of how does a branching mind perceive a branching universe? And that turns out to be what gives one kind of essentially what gives one quantum mechanics. There are details there that still to be worked out, but at a qualitative level, that's the story, is that it is, and then it becomes very critical that we have this idea that we have a single thread of existence, because that's what causes us to be forced to knit together all these different threads of time. So anyway, the final part of the rabbit hole, descending down to the rabbit hole, is that, so we have all these possible rewrites are happening. They define different threads of time and so on. But then you might ask yourself, what a confusing situation. We've got all these things happening. We've got this rule, and we can hold in our hands the rule for the universe. And we say, look, it's rule number 156 or something. And that's a very bizarre possibility that we could just say, our whole universe, we got rule number 156. Mm-hmm. And another universe might have got another rule. And it's then very mysterious why we got a rule that's kind of a low-numbered rule, not a rule so complicated that we can never make a prediction about what happens in the universe, because we're always, sampling a different part of the rule and so on. So I was very confused about this for a while, but then I realized actually the right way to think about it is the universe is running all possible rules. And that's what the Ruliad is this a universe that is, where you could slice it to look at just the space part, you can slice it to look at the quantum mechanics part, but in the end, it's running all possible rules. And the big fact is that knowing that to an observer like us, there are certain necessary features of the perceptions that we have about the universe. So the universe is ultimately just this Ruliad that's doing all these crazy things, but as a computationally bounded, believing you're persistent in time observer, there are certain necessary features of what you perceive about that universe. And those necessary features turn out to be exactly the big theories of 20th century physics, which I think is really, really interesting because it's kind of like it's on us, so to speak. But it's not completely on us. It's any observer who has these general attributes that are like us will conclude these particular things about physics. And so, that's a sense in which both the universe is inevitable and the universe is dependent on the way we particularly are. But I was going to say, in this kind of picture, so a particle in this kind of picture is this kind of lump of kind of structure in this graph that can move without change through time. So now the question is in Rulial space, and this is where it kind of philosophy meets science in some strange way. In Rulial space, you've got two minds that are at different places in Rulial space. And you can always translate between them, just like you can translate between two different computers, two different Turing machines. There is a way of translating between them. But if you ask, what can you propagate? What thing can be produced by one mind and kind of move unchanged through Rulial space and land at the other mind? I think that again, not fully worked out, but I think concepts are the packaging of thought that get to be transportable like particles through, in this case, Rulial space rather than physical space. So in other words, you take what's in your mind and there are all these neuron firings that are happening and so on, and then you say a word, you elicit some kind of concept, and that's a thing that's packaged enough that it can arrive at my mind and be unpacked, and it's kind of the same thing in some sense. It's kind of the analog of motion, this idea that there can be a kind of a lump of stuff that is translated from one mind to another. I think that's kind of that's something one can think about as kind of that's sort of the analog of particles. It's a very bizarre idea that the analog of an electron in physical space is a concept. So that was a bit. We were pretty deep in this rabbit hole.
No,
it's
that's fine, Stephen. I'm a very curious person, and I just asked you what the Ruliad was. I thought that you were going to say that it was some sort of object from mythology. Maybe that's where the word came from. But I now have like 10,000 more questions, which makes this very difficult because I'm very interested in philosophy of physics as well as philosophy of mathematics. But the reason that I asked you about the Ruliad in the first place was because I was struck by the language that you used in describing it, and my own Rulial vocabulary is not fully developed. I'm not a master of it yet. But what I was struck by was the way that you described mathematicians. You described them as observers who are like looking at this portion of, I'm not sure if it was Rulial space or metamathematical space. And what struck me about
mathematical space is a slice of Rulial space.
Right. That's what I thought. And What struck me about this is that this language is very reminiscent to me of uh, conventional sort of Platonist language in the philosophy of mathematics, where people like Gödel is a great example. He believed that there's
Yeah.
a universe of sets where these mathematical objects, it's abstract, but they sort of, for all intents and purposes, they live there. We can sort of observe sets and the structures they create, almost like we would observe like a house or a chair or something like that.
Yep.
And what I'm wondering then is just how you think of the ontology or the existence of these
Right.
mathematical objects. And we've really strayed very far from ChatGPT, but this is quite interesting. So I'd like to finish on this before maybe we move
Yeah.
back.
Yeah. Right. So one of the things that this question, does mathematics exist? Is there a Platonic kind of existence, some fundamental ontological existence to mathematics? And the thing that I realized a year or two ago is basically in my theory of how things work, if we're going to say the physical world exists, we have to say mathematics exists as well. They're the same thing. In the end, they're both samplings of the Ruliad. One is sampling by physical observers, another is sampling by kind of mathematical observers. Physical observers are very concerned about time and the progression of time. Mathematical observers less concerned with that. They're more concerned with kind of a more almost a spatial in the meta-mathematical sense of just putting theorems in a bag and saying these are the theorems we think are true, so to speak. So yes, I think my kind of the sort of the quick version would be, mathematics exists. If we believe the physical universe exists, we have to believe in the sort of Platonic existence of some sort of a thing that exists that is mathematics, so to speak. And by the way, there are many consequences of that. I mean, like, for example, here's an example of an interesting thing. So one asks, what are possible axioms for mathematics? Like, is the continuum hypothesis and set theory? Is it true? Is it not true? And one of the things that can be interesting here is, given the constraint that we have human-like mathematical observers, it could be the case that there are certain axiom systems that are compatible with our way of sampling the Ruliad and others that are not. So, for example, I mentioned, can you operate mathematics at the fluid level, at this kind of high level, or do you get shredded down to talking about, this is the way we define real numbers and so on? It could be that, for observers like us, there are certain axioms that are viable and other ones that if you use those axioms, then there isn't a sort of continuum version of what's happening in mathematics. There is no fluid representation of mathematics. You will be forced down into this kind of shredded level where you're having to discuss all these axiomatic and subaxiomatic kinds of things. So it really has consequences to have, this view of sort of the structure of mathematics has, in a sense, practical consequences in the way that you think about it. One of the things that I've been interested in a long time is when I look at computational systems, undecidability shows up at every turn. And, perhaps, a piece of personal history back in the early 80s when I was working on this, I was working at the Institute for Advanced Study in Princeton.
Automata.
Yeah, right. And I was studying these things, and there were a number of very good and well-known mathematicians there who got really interested in what I was doing. And they were like, these are really simple systems. We can solve them with mathematics. We're just going to, we're going to figure them out. And they tried, and it just didn't work. And, they were not used to that. They're used to the idea that in mathematics, you have these structures and you don't get blocked by essentially undecidability or what I would now see as computational irreducibility. I think my main achievement, as I realized looking back on it, was to realize that the fact that you get blocked is itself a very interesting fact. That, the fact that there is this computational irreducibility block to progress of a kind of traditional mathematical kind is itself interesting. But what was surprising there was that in these computational systems, you're all the time, you're thrown into undecidability, you're thrown into computational irreducibility. And yet working mathematicians, don't worry about undecidability at every turn.
Right.
How is it that mathematics can be done without falling into this undecidability? And the answer, I think, is this kind of fluid dynamics view of mathematics, that, undecidability is what happens when you're down at the level of the molecules.
Right.
But once you're at the level of the sort of fluid dynamics level, it's just like, you ask, well, what's going to happen in this gas? Well, we know the gas laws, we know the laws of fluid dynamics, we can say what's going to happen at that level. It's actually quite simple. It's quite computationally reducible. But if we say what's going to happen in the individual molecules, that's really hard and we can't figure it out. And that's that's kind of what's happening, is that there is a higher level mathematics, is why mathematicians don't, and that's the level that mathematicians operate at. That's why mathematicians aren't continually being dragged down by undecidability.
Right. But of course, the mathematical logicians, the set theorists, the recursion theorists, the people who are working with the atoms, so to speak, they are, of course, encountering the undecidability.
Absolutely.
And I think it was Paul Erdős. He said once, like, "Oh, the demon of undecidability rears its ugly head again." Something like that.
I talked to Paul Erdős about undecidability on multiple occasions.
Okay.
And I was really curious whether he thought that the mathematics that people have done is kind of, if you go to these difficult problems in math, how many of them are going to turn out to be undecidable, and how many of them are just, you have to be a little bit clever and you're going to get it. Mm-hmm. It's kind of like if you do integer equations, Diophantine equations, it's kind of like, is there, in computing, there's been this kind of Moore's law of you always get faster chips every so often, right? And so you can ask the question, do you always get better Diophantine equation solving technology if you go a few more centuries? And, we went from linear ones in antiquity to quadratic ones at the beginning of the 1800s to elliptic ones in the early 1900s and so on, but we know that eventually you will get to undecidability. The question is, how close at hand is it? Are practical problems that mathematicians are,
right,
bumping into, are they in fact examples of undecidability?
Right.
I couldn't get Erdős to sit still for long enough to really have an interesting answer to that question. Mm-hmm. He kept on, in the conversations I had with him, whenever it was like, let's talk about the general question of whether this whole bucket of problems has this feature of being right up against undecidability, his personal response was always, let me tell you about another specific problem. So it's kind of like, and in a sense, to me, that's almost a sign of that's the answer, because it's kind of like I'll give you an example. In our Wolfram Language, Mathematica computational system, we solve equations. And one of the big results in, Tarski's decision theorem from the 1940s, I guess, shows that for any equation over the reals or complexes, there is a systematic procedure for solving that equation. Mm-hmm. It's not, it's a decidable thing. It turns out, we figured out great new algorithms for doing it, but it's decidable. For Diophantine equations involving the integers, we know it's not in general decidable. And so one question would be, on the ground, when you're writing code, what is the effect of that? And the answer is, for sort of real and complex equations, it's a big industrial algorithm that just grinds through and does everything. Diophantine equations, it's more like the Erdős approach, which is you're breaking into a zillion different cases for all these different kinds of equations. That's the kind of on the ground signature of undecidability when you're actually trying to do things. And I think that was sort of, in a sense, as I think about it, as I'm describing this to you, that's kind of what, in a sense, the very fact that Erdős, kept on just saying, let me tell you about this one other problem, let me tell you about this one other problem type thing, was almost a sign that it is the case that in certain kinds of areas of mathematics, you have bumped into walls that are sort of pieces of undecidability.
Mm-hmm. Now, of course, like we just mentioned, the mathematicians the mathematical logicians, they deal with undecidability all the time. So you mentioned the continuum hypothesis. We know that that's independent of ZFC, but also, as you mentioned, the higher level mathematicians haven't really encountered it yet. And Tarski's last student, actually, his name is Chaim Gaifman. He's a mathematician at Columbia. He's sort of my mathematician / philosophy father, my mentor. He's actually the one that told me about what Paul Erdős said about independence rearing its ugly head. He was in the room with Paul Erdős at the time that he said that. But he's always told me how much he wants the twin prime conjecture to be found independent or undecidable because of the absolute earthquakes that would send through all of mathematics. Because so many, all of working mathematicians are working, laboring under the assumption that there are solutions to the problems that they're working on. And if all of a sudden you have this phenomenon where the twin prime conjecture, like one of the biggest open problems, is just not solvable anymore, then all of these open problems become very frightening, and you no longer are working under this.
Right. But it's a little bit interesting because, like, I remember I ran into Andrew Wiles shortly after, the Fermat's last theorem thing.
Great.
And I said, so what axiom system is this proof based on?
Mm-hmm.
He says, I don't know. Says it's probably got some set theory in it. I'm not sure. Maybe it's just beyond arithmetic. I don't really know. And it's interesting because he doesn't care either. That is, it's not, this is the fluid dynamics level of mathematics.
Yeah.
It's, what can you conclude? And this is the, that's what mathematics, as mathematicians enjoy practicing it, is typically about. And, saying, well, it could be the case. The twin prime conjecture is true if you have some large cardinal thing, and it isn't true otherwise. And it's, it's derivable if you have some large cardinal thing, and it isn't derivable otherwise, and so on. And that, I'm not sure how much of Gödel's theorem had a bigger effect on mathematics probably than a discovery of really low-hanging undecidability would probably have today. And the reason I think for that is that at the time, kind of Hilbert's program had been very much we got it, mathematics is just going to be formalized, it's just going to be a giant machine, and we're going to be able to crank out true theorems. And that was the point of view that people had, okay, this is what mathematics really is. And that kind of got smashed. But people were really into that at that time. The thing today is, I just don't think, I think, in terms of the practical sort of fluid dynamics level of mathematics, I don't think trouble at the atomic level is going to, the question of, here's the thing. We look at actual fluid dynamics and we ask the question, when does it matter that there are molecules in fluid dynamics? And the answer is, if you're a space shuttle entering the Earth's atmosphere in hypersonic flight, it matters that there are molecules. Mm-hmm. The shock waves thinner than the mean free path, and so on, and it matters. And so there are these corners of fluid dynamics where it really matters. And I guess the question would be, is it? I think mathematics would go on. I think it's very likely to be the case that a lot of these currently unsolved problems are independent of the axioms that we've currently defined, and it's an interesting sort of almost sociological question. What effect would that have? I mean, I've been polling for the last 40 years. I've been polling number theorists for the following question, which is, where is the boundary of undecidability in Diophantine equations? In fact, I just ran into a number theorist just a few days ago, and I polled her about the exact same thing. And, is it the case that right above where we know how to solve Diophantine equations now, we'll run into undecidability? Or do we have to go to these really complicated, elaborate equations before we get to it? My guess is it's very low lying, just above where we've got right now, we'll run into undecidability. I think the more common statement from number theorists is it's far away. I don't think they're right about that. And kind of a signature of that, if you're actually doing Diophantine equations, is you say, okay, I've got this equation. It has a solution, or it doesn't. Say how big are the numbers that are in that solution? If those numbers are absolutely huge, that's kind of a little bit of incipient undecidability showing up. It's kind of like if I were just imagining a procedure where I'm going to solve this equation, it's kind of like I might start and I just might look at bigger and bigger numbers. The fact that the actual numbers that solve it are huge numbers of digits long is kind of a sign that I'm kind of entering the domain where I've got lots of computation I have to do to find out the answer.
Okay, well, I have one more follow-up about the Ruliad, related to the Ruliad and
please.
space. So the physicists are interested in observing the physical dimensions, for lack of maybe a better word, of Rulial space. And then and you said they're interested in things like time and electrons and this sort of thing. And mathematicians are interested in the metamathematical slice of Rulial space. Now, and I'm sorry for dropping so many names, but I feel like I need to quote people when I'm talking about them. I was talking to Joel David Hampkins. He's the person with whom I had this episode on the Set Theoretic Multiverse, and he is very much a Platonist through and through. And he was saying that, I think he like picked up a cup or something like that and said, I really have no idea what this cup is or how I might explain its existence. Quantum mechanics, all of this is quite foreign to me, and I can't wrap my head around it. But then if you take the empty set, it is quite easily characterizable. We know its essential properties or something like that. We know that it is the set that has no members. And what I'm wondering is, in your picture of the Ruliad, do mathematicians gain access to this metamathematical slice because they have acquaintance with the properties of its objects? Because they can't well, maybe you do think they can directly observe it. They can see, hear, and touch it. But maybe that is your
I think
answer.
they can observe it just in the same sense that we can observe the physical universe.
Okay, yeah,
in many
please
ways.
elaborate on that.
Yeah, I mean, so, well, let's see where to start. I mean, first point is, one is used to the idea in science that science is merely a modeling, a representation of the world. Right? That it is, we have a model, I've got my model, you've got your model, they're all approximate representations of the world. So the first thing that is a bit of a shocker is if you actually think you've got the theory of physics, right? You've turned physics into a branch of mathematics. You're no longer talking about modeling and, this version, that version. You've got a thing that is a complete representation of physical reality. Now, there's a trickier thing with the Ruliad, because we're saying there's a representation in a sense of all possible physical realities, but we are contingently happen to be situated in this place in Rulial space with these characteristics as observers, and so this is what we are observing. Now, in terms of how we parse the Ruliad, how we understand what's there, we are part of it. And so a thing that I've been developing, actually, I got sidetracked the last few months on AI kinds of things, but absent that, I was steaming along producing this thing that I call observer theory, which is kind of as Turing machines are to the theory of computation, so sort of observer theory is a kind of general representation, a general idealization of what it means. It's kind of a computation theory for observation, so to speak. It's kind of what it means to be an observer. And roughly what it means to be an observer is there's a lot of complicated stuff going on in the world. We're trying to stuff it into our minds. Our minds are finite. We have to simplify what we see going on. We have to equivalence many microscopically different things that are going on. We have to treat as equivalent for purposes of stuffing them into our finite minds. And so, a simple example would be, you got a gas, it's got a bunch of molecules bouncing around, there's a piston on one side of a box that's trying to measure pressure. There are many different ways that the molecules can hit that piston, but all we care about if we're measuring pressure is the aggregate effect of all those molecules pushing on the piston. And that's the characteristic of sort of all the different kinds of measurement we're doing, whether it's vision, whether it's, all sorts of other kinds of things. It always has this characteristic. The world's a complicated place, but we're just taking a sampling of that, and we're taking a certain sampling that we care about. So that's our view of what's going on in the Ruliad, is this sampling. And then the question is, and we can deduce, we can have a theory based on that sampling. We can say we know, the sampling is like this now, it's going to evolve in this way, et cetera, et cetera, et cetera. We can have that point of view. Now, you ask the question, what is the difference between that kind of sampling of the physical world, sampling this abstract Ruliad for purposes of our physical perception, and sampling the abstract Ruliad for purposes of our mathematical perception? And I think the answer is there's not a lot of difference. And the fact that we can, one non-obvious fact is that sort of understandable perception is possible. It could be the case that this sort of unruly Ruliad, so to speak, this Ruliad full of all this complicated stuff, that the things we're interested in for our physical experience, or for that matter for mathematics, just rub our noses in all that complexity. That we just have no way to take all that complexity of what's going on and stuff it into our finite minds. So it is a non-trivial fact. It's a scientific, potentially scientific fact, partly scientific, partly it's a sort of contingent fact associated with the way we are as observers, that it is possible to take all that complexity out there and kind of compress it into what our finite minds can deal with. But I think that the way that we think about kind of that observation, the way we think about being an observer, a physical observer, I see it as being really no different than the way one might think about a mathematical observer, except for the fact that there are detailed differences in what in what the mathematical observer is sampling versus what the physical observer is sampling. So I do tend to think that kind of the things of mathematics are, in some sense, everything is as abstract as everything else. I mean, if you say, what is an electron? Say, what is a cup, you were saying? I can pick it up. Okay, great. What really is it? Well, what it is this complicated, sort of engram of things in this hypergraph, and the hypergraph is continually evolving, and it's leaving this structure that more or less stays the same over time, and it's an abstract thing. We think of it, we've managed to perceive it as a cup, but if we say, what really is it? It's really this pattern of connections in this hypergraph that's evolving in this way, and we, from our view as observers, choose to think of it as a cup. But it's, what it, quotes, really is this deeply abstract thing. And this is what happens when you have a sort of truly fundamental theory of physics. You get to say the physical world is made of these things that are just abstract things, so to speak. I mean, there is no difference in the end between the kind of the physically realized. Okay, so this gets a little bit more tangled, because one of the key points is that we are part of this abstract system. And so, when we say it is a physically real thing, that means that it has certain effects on us and our perception of things. And that's our perception of what reality is. But in some sense, we can untangle it, and we just say it's actually a bunch of atoms of space, and they're interacting in this way and that way. And ultimately, it's something that looks just like that thing over here in mathematics that is something we would normally call an abstract thing.
Well, I'd like now to take us back full circle to where we started on this fascinating tangent. But so you've said that, and correct me, of course, if I'm wrong, that our mathematics is a very human sampling of this one dimension of Rulial space, namely the metamathematical space. But at the same time, the way that we got started talking about this is, you said that ChatGPT and Wolfram Alpha and perhaps its successors will displace much of human mathematical and STEM activity. And I wonder how you reconcile these two statements.
Right. Okay, once you've decided what tower you want to build, computation, and more so than the kind of the ChatGPT kind of world, that once you decide on the tower can be automatically built for you. The question of which tower you choose is not something that is a human question. That's a question that comes out of the kind of web of human history and so on. That's not, we can say to ChatGPT, based on what you've seen on the web, what would a typical human choose now? That's one thing, but there is an arbitrariness to what we choose next, which is an artistic kind of arbitrariness. It's a kind of an arbitrariness that is, we made this choice.
It's driven by aesthetics and other concerns.
Yes. Yeah, right. It's driven by this sort of web of things that is our sort of human history and existence. And I think that's the sense in which. So what I would say is the deep dive, the drilling, the kind of So how do we work out? Given something like, I don't know, in our physics project, given some particular rules for hypergraph rewriting, what are the consequences of those rules? Okay, we just run it on a computer. We run, a billion steps on a computer. We see what happens. And it's not we're going to think about it mathematically. It's just run it and see what happens. And I think that I think as a more practical matter, a lot of learning in sort of STEM areas has to do with learning the mechanics of how to solve problems in those areas. And there's a lot of technology that's sort of conceptual technologies that have been built up in doing that. And the point that I guess I was making there was a very practical point that, you can say the only way to climb this sort of tower of capability is to learn all that stuff yourself. But that's becoming decreasingly necessary because we've managed to automate the climbing of the tower. We have not automated and will not automate the choice of which tower is out there to climb, which tower we choose to build, which tower we choose to climb, so to speak. So I think that's the distinction. I think it's an interesting, we ask the question, will we eventually automate everything? It's kind of a fun, I give you an interesting sort of exercise of philosophy meets the real world is some particular blockchain where the founder of this blockchain is like very interested in formalized mathematics. I think he's told me because he sort of thinks that to know how his blockchain can be governed and to make sure that the governance of the blockchain is going to be just right, he's going to base its principles on set theory. Now, this is an interesting philosophical kind of consideration. You're thinking about how do you govern something in the world that is sort of a human set of choices about how you set up, I don't know what, what amounts to the laws of the blockchain, the ethics of the blockchain or something. And you say, well, can you base that on set theory? And the answer is there's nothing special about set theory there. There are infinite number of possible kind of axiom systems you might choose that might or might not correspond to what we think are worthwhile kind of human level laws. And I think the thing to realize from that is, if you say, what is it that we are ultimately trying to do as a species or something, what is the ultimate goal of everything? That's not something for which there is going to be some proof in set theory of what the answer is. Mm-hmm. It is just not the right kind of a thing. It's, the purely formal does not answer that question. That question is ultimately a human question of, which way do we choose to go? And that's kind of I think, that's the ultimate thing that doesn't get automated by AI. AI might choose, sadly in some ways, to regress us to the mean by saying, look, this is what everybody else put on the web. Now the right thing to do is X because that's what everybody else has done in the past. But that isn't, that has not been, that isn't the most interesting kind of aspect of the way human history works.
Mm-hmm. Returning to, this metaphor of humans selecting the tower that we want to build and then having the AI build it for us. And you said that this is motivated by many reasons, but for lack of a better paraphrase, we can just say it's because of our humanity. That's how we decide which tower we want to build. Do you then envision us still, even though we're no longer maybe solving the technical problems, but we would still be very much interested in understanding the tower after it has been built? So we might still want to, in the same way that mathematical Platonists consider themselves to be investigating these structures that are already out there. They don't think of mathematics as constructive. Will we still be interested in exploring this segment of metamathematical space in the Ruliad that's been unearthed for us?
Yeah, I think it's what can you stuff into your mind? It's fun to stuff things into one's mind. Yeah. And that's, this is what this is about, is kind of, what can we take from the Ruliad and stuff in our minds and kind of figure out how we, essentially what we're trying to do is we're trying to find pockets of reducibility in the Ruliad where we can understand what's going on well enough to be able to stuff it into our finite minds. Now, one of the more sort of, I would say, interesting things is the progression of kind of our understanding of things we can think of as a kind of progressive colonization of Rulial space. That is, there was a time where we only understood this one very thin, way of thinking about the world. And progressively, as we invent new paradigms for thinking about things, we get to sort of expand our domain in Rulial space. Just like, we send out spacecraft to expand our domain in physical space. So as we develop new paradigms, we're expanding our domain. And so you might say, well, gosh, in the infinite future, what does the infinite future look like? Well, maybe we'll understand everything. We'll have expanded throughout Rulial space. We will have, but in fact, one of the sort of Pyrrhic features of that situation is if you manage to stuff all of Rulial space into your mind has kind of exploded. You no longer have, one of the things that's important to us is a certain degree of coherence of our minds, which is what I think is tantamount to our belief in our existence, so to speak. The fact that we have a coherent existence is a consequence of the fact that we have a fairly specific point of view, so to speak. As soon as we say we've managed to spread ourselves throughout the Ruliad, I think that the sort of the Pyrrhic situation is, well, that's all very well and good, but then we don't really exist. We don't have the same sort of feeling of existence that we normally do as a kind of a coherent sort of single thread of experience of what's happening in the universe. So it's kind of but I do think that this process of, so where do you choose to go? That is a sort of quintessentially arbitrary and quintessentially a human kind of thing. That's a thing that, if you say, okay, AI, go, I've spent a significant part of my life studying the computational universe, the universe of all possible computations. And one of the things that's a bit shocking about that is you can jump to another part of Rulial space. You can just run a program that's nothing like, that's just an arbitrarily chosen program. What you discover if you do that is it's in some sense disorienting. The thing you get is something you can say, I can see how the bits work, and I can see, it looks kind of complicated to me. But we don't have a human connection with that. There is no human narrative of the kind that we're used to in natural science or something like this. It is just this weird thing out there in Rulial space that is very unconnected to this sort of thread of development of science and intellectual kind of history that we as humans have. So it's kind of it's kind of like you're seeing the aliens, so to speak. The aliens are, the aliens are out there in Rulial space, and you can quite easily sample them. But the thing you find is you don't have a human connection to these things. I think that's the and so it's in a sense finding these little paths to certain parts of Rulial space. That is in a sense the meta kind of concept of the expansion of science and human knowledge is kind of, how do you populate more of Rulial space? How do you colonize more of Rulial space?
This has been a very fun digression on the philosophy of math and philosophy of physics, and maybe at some point we will be able to sit down and talk more devotedly to these topics, because I would love to hear about your thoughts on revolutions, maybe more on set theory and foundations too, and philosophy of physics, time, space, all of these things. But for now, since we started with ChatGPT, that's where I'd like to go back at least for a little while. And particularly, I have in mind your objection to this blockhead thought experiment, if you can rewind your mind about an hour. And one of your objections was that this thought experiment, any given instance of it, any time we run this hypothetical Turing test, it's finite. But the way that I would respond is that, and this might even be a response that Ned Block gives, is that we don't last forever either. And all the argument has to show is that in theory, there are machines that could pass any feasible iteration of the Turing test, and that we would also argue or intuitively believe are not intelligent. And that this in itself is sufficient to substantiate the thesis that I think he labels it as psychologism, but it's that intelligence cannot be solely determined by behavior, but must be informed or determined by the sort of information processing that is going on internal to the machine.
I find that amusing,
That's
because
good.
if we imagine kind of looking at, the future fMRI machine, the thing that's measuring, every nerve impulse in our brains, and we're looking at all of this, and it's a big mass of stuff. And we say, look, it's amazing. It's truly intelligent. It's not just, a simple machine-like thing. Do you really think that there's if we, and then somebody will say, but actually, look, it's based on these simple rules. It's just running these rules. And look, we can see it's just running these rules. So there's nothing there. And we'd say that about a brain. So the question is, what's the, right. So that's kind of in the end, that's saying, if you're kind of making the argument, if you can understand the mechanism, then there can't be anything there. And what I'm saying is computational irreducibility is the statement that understanding the base mechanism is not enough.
Mm-hmm.
Right? That there's an irreducible separation between the base mechanism and what actually happens. It's in a sense, in the theory of physics that we have, the progress of time is achieving something. It isn't the case that you go through time and it's just, we already knew what was going to happen. Time is, there's something really happening in the progress of time, so to speak. And I think that's kind of how I would respond to this, that to say that the fact that there is a mechanism down there, we can see it, is it that the all the things have been pre-generated and we're just, by the way, I mean, if we start taking this experiment literally, we got this great big library of all these conversations. Well, now I need to think, what's the mechanism by which I actually access these things? It's pretty big. It's probably going to be, many times the size of the universe. I got to go and I got to start thinking, how do we're talking mechanism here. So let's talk mechanism. How do I actually go find the right conversation? Got to have some system. It's got to do matching. It's got to do this. It's, in the end, it's doing a computation just to find it. Just saying, we've got this library, if we're really going for mechanism, isn't good enough. So I'm going to say that I think this thing about we can see the mechanism, so we've nailed it, we know what's going on, that is a mistake of not understanding computational irreducibility. And I think it's and it is, I think computational irreducibility, it's also the kind of free will versus determinism question. If you know the underlying rules, does that mean you have no free will? Does that mean you are, robotically determined in what you will do? Well, at some level, it can say that. But as a practical matter, if I know that that if I know you're operating according to certain rules, I can say, well, I know what you're going to do. But no, I don't, because I can't run those rules any faster than you're running those rules. So I get to find out what you're going to do at just the same time as you get to find out what you're going to do. I have to say, I was just a few weeks ago, I happened to see, we're talking philosophers here, I happened to run into David Chalmers, and we realized we'd run into each other like 30 years earlier. We started having this conversation about free will, actually. And what's really amusing is that here we are, we're discussing, he's talking about how we really have free will. There's really some essence of free will. And we're realizing we just had the same conversation that we had 30 years ago. It was a determined, given the initial conditions of these two humans, it deterministically went the same way.
Mm-hmm. Well, I find myself agreeing with you, I think, pretty much completely. I guess, again, doing another loop in our conversation, when I first asked you this line of questions, you pointed out that intelligence is really just a word. And I am inclined to think that it's, even though it's quite useful to us, it is a very problematic concept and is really more a byproduct of our lack of understanding purportedly intelligent creatures like humans. For instance, so it was once thought that for a computer to defeat a person at checkers, it had to be intelligent. But when it finally did, we decided it wasn't intelligent. And it was the same with chess and then Go. And it's, if ChatGPT can beat the Turing test now, then it's a similar story with ChatGPT. And
Oh, sure.
right. And I think it
No, I mean, I
comes
think
down to
that
this
the thing that's
mechanism.
the shocker there, sorry, the thing that's the shocker is people say there's something magic about, writing essays, there's something magic about doing calculus, whatever else, right? And then one makes a system that does it, and people look inside and they say, my gosh, there's no magic here.
Exactly.
Well, we haven't quite been able to do that for brains yet. Eventually we will be able to do that. And we'll realize it's just a bunch of nerve firings. And it's like, by golly, there's no magic here.
Yeah.
And it's kind of like, it's going to be the exact same thing. It's just we haven't happened to be able to, we don't imagine that we can look inside brains in the same way that we at least imagine we can look inside the workings of ChatGPT. The fact is, I've dissected a bit what happens inside ChatGPT. It's pretty hard to understand. It is probably very similar to what it would be like if I were to, see the signals inside a brain. It's kind of like things are happening here. And, in the end, the sort of the net of that is something that is very human-like and we would kind of recognize. But at the microscopic level, it's just, one interesting question is there a natural science that is intermediate between kind of the individual nerve firings, the individual artificial neural network kind of things, and the overall emergent behavior? Is there, for example, in neuroscience, it's been a long-running key problem of neuroscience, is there a kind of language of the brain that is intermediate between, the electrophysiology of a nerve cell is this, and, human psychology works this way? Nobody's really found that intermediate level of description in neuroscience. Whether it exists or not is not clear. And the point is, but the fact that there's this kind of separation between the underlying kind of rules and the sort of emergent behavior, that's the surprising, that's the intuitional surprising thing. That's the thing, I've encountered many kinds of people, even philosophers over time, who I remember we have a summer school every year we've been doing for like 21 years now or something. And we've had various philosophers at our summer school. I remember one particular one who had never really touched a computer. And I said, you will not understand what's going on unless you actually do this, your own fingers, type, and, actually run these things and see what happens. And, it's just like, wow, this is really, it's not what you expect. It's like you have a certain intuition about how the world works. You actually see what happens in these computational systems. They don't work the way you think they're going to work. We have an intuition from engineering. We say, you say, I want to make a really complicated thing. Say, okay, you're going to have a complicated plan. It's got all these gears and levers and so on. It's going to be a complicated machine. The idea that a machine with a simple construction can do complicated things is just something, I mean, I've sort of gotten used to it after a few decades, but it's something very, very surprising and shocking for us humans in terms of our traditional intuition. And that's, it's the same kind of thing, it's the intuitional gap that computational irreducibility brings. And by the way, in terms of sort of the progress of society and so on, and asking, okay, for example, let's say we're going to make AI ethics. We're going to make a perfect AI ethics. We're going to make something where we're going to put guardrails around AIs and they're never going to do the wrong thing. That is charmingly similar to Gödel's theorem. What goes wrong with that? That is, Gödel, you could say, said, I want to make just the integers and nothing but the integers, and nothing will go wrong. And what Gödel effectively showed is, you can keep patching with an infinite number of laws, but you'll never actually get the thing you thought you wanted. And it's the same kind of thing with kind of thinking about sort of how do you patch up AI ethics. And so, I mean, things like, I have come to the opinion that, computational irreducibility is one of these intuitional steps that's going to kind of affect a huge number of things that are really important to the way we think about the world. it's kind of one of these things that is sort of, it's a piece of intuition one needs to get, and without it, one's led astray on lots of kinds of issues.
Well, it's always a nice feeling when I find myself in lockstep thought with my guest at the end of one of these conversations, because even before, you just mentioned this idea of looking into the mind and finding no magic there. And even before we were like an hour or so before we started talking and I was thinking about these topics, I was thinking about this thought experiment that, as a future philosopher of some sort, I do this sometimes. I have thought experiments. I was thinking about some neuroscientist brainwashed so that he doesn't realize that he's a human. Then he has access to all the information about the brain, and he witnesses two humans interact, and he would say, well, these things aren't intelligent. Just look at how this is how they work. We have the mechanisms and everything. There's no magic, nothing special here. So I'm glad that we've ended up in the same spot. And naturally, I wanted to talk about all sorts of other things too. You mentioned Chalmers. I had a lot of questions about ChatGPT and the extended mind, which is a theory he came up with Andy Clark. But we've really run the gamut.
We probably run out of time, but I want to know what that theory is, because I don't know what that theory is. So tell me what that theory is.
Oh, the extended mind theory is roughly the idea that our minds are not identical to our brains, and that our minds, in fact, extend beyond our skulls, so that when we think with our fingers, or when we're using a calculator or write on paper, these external processes are also parts of our mind, because they're bona fide, cognitive processes. And obviously their paper, Chalmers and Clark, goes into a lot more detail, and there's a lot more work on it. There's embodied cognition, active cognition, extended cognition. But I thought there were some interesting questions here regarding Wolfram Alpha, ChatGPT, their integration, and their potential integration with the human mind, both externally and perhaps in the future internally.
No, it is interesting to think about, when we have, not just the visual interface, not just the, if we can directly connect, those nerve firings into what's happening computationally, what will that feel like? What will it be like to be able to think a thought and have something happen, so to speak? Well, it's actually not that different from what we get to do with we think a thought and our fingers move type thing. But anyway, very interesting topics. All right, we'll have to do this again sometime. I've had a good time.
Hold on, Geeslings. Before you go, please like, subscribe, follow if you haven't already. Smash all those buttons. And also, if you haven't followed me on Twitter at Robinson Earhart, or if you're not joining me every morning as I eat my pint of ice cream on Twitch at Robinson Earhart on Robinson Eats, please do so.